This speaker is Professor Sebastian Szybka from Jagiellonian University, and he'll tell us about standing waves. Please.
Thank you for invitation. And I will tell you about standing waves, standing gravitational waves, and our research. So I'm Sebastian Szybka, but this project is a joint project with Cornelia Nickel. Cornelia Nickel is, she's a student in Krakow. Okay, and I'm going to talk about linearized Chandrasekhar and Halilsoy standing waves. So maybe I will start with the motivation, because when I was in Warsaw many years ago, I think Professor Jagiellonian told me that it's more interesting to hear why I did something, not exactly about the details. So I will start with a brief introduction. Okay, so what are standing waves? I think all of us know, more or less. So the most basic thing is when you play a guitar and you have a string in the guitar and there is a standing wave on the string. But the standing waves appear in different contexts. And when I try to find in the history of physics where they appear for the first time, you may guess that it was a long time ago. It was Leonardo da Vinci, more than 500 years ago. It's an amazing story because many people, I mean, everyone in the history of humanity had to eat breakfast. Yes, that's ordinary thing. But among all these people, only Leonardo da Vinci noticed the following thing. When he finished his breakfast and there were some crumbs on the table, when he hit table with his hand, the crumbles didn't distribute randomly, but he noticed that there are some patterns. And in one of his notebooks, he write down that this is his observation, but he never found a solution to that. Okay, and then there was another person who was studying this. Nowadays, we know that those are just mechanical standing waves on the table. When you press the table or hit it, there are such standing waves, and there are nodes and antinodes, and this force comes to move not in a totally random way, but to have some patterns. But when this kind of standing waves make, I would say, a career in the world, it was because of Chladni. It was end of the 19th century and beginning of the end of the 18th century and beginning of the 19th century. They were known as so-called Chladni figures. And you may find not photos, but drawings of these figures. Imagine that you have a plate like this. You put some dust on this, and then you have a bow, like a bow you use for playing violin. And you move it, then there are mechanical vibrations. And people did not understand that at that time, but they observed different patterns, like, you know, the dust moving this way, for example, or depending on the material, depending on the size of the thing, depending on how strong you move the ball, there were different figures. And it was like, I would say, a social thing. So they show this to other people as a truth. But this was moved to another level by Faraday. In 1831, when he did something similar, but with a fluid. So you have something like a plate, you put it on something, and then you have vibrations here. And now you look at the patterns that appear on the surface of this fluid. And you can have different So there's this paper from 1931 where he showed these patterns and they look like this. There are many different patterns. Or it was like this. I mean, there was a plenty of them, so you can draw almost anything. And it was a question how to explain it. So a few years later, Navier-Stokes equations appeared to describe this system. And people are working on this up today. And it's like a hard computational problem. So what do you see here? Here you have the force with some amplitude and some frequency and the shape, particular shape of the amplitude, how it's changing. And then you have different configurations. And when you move the amplitude of the force above some limit, I mean, this configuration exists because of the nonlinear phenomena in the fluid. Okay, so when you assume just the amplitude is small, then you don't see very spectacular things. But when the amplitude is large, then the nonlinear things enter, and the nonlinear physics is here, and this is hard to compute this. And there are people, as I said, still working on the problem. There is a water journal when they make experiments with water, other fluids, and try to understand that. Now, there is another thing related to that, so-called we call it walkers. Droplet walkers. And there was a paper in Nature, I think, around 2005, when they observed the following thing. And you can do that even in this room. I have a tool for that, but maybe later. It's not so easy. This is the Tibetan bow. We put some water inside, and it has particular frequency. You move, there is a standing wave inside, and if the amplitude is large, then some drops will jump above the surface of water and they will fly. And the people, this paper in Nature was about interaction of this walking thing, because there is an interaction with the water, it's flying above the water, and with other droplets. And they claim that they could make analog of some quantum phenomena, but these results from this Nature paper were not repeated, so it's not exactly true. But anyway, the physics is very interesting. So now, I mean, if you think about this kind of system, so you take a mechanical system, you take the fluid, water, and whatever. So the most basic question is, what will happen if you will take space-time? Yes, because it will oscillate in some way, and the question is, what kind of patterns will appear in this oscillation? And now you can think about if this kind of a system, if you think about space-time could be somehow realized in nature. And one natural field where this kind of thing could appear is in cosmology, and you have so-called Gaudi solutions. And the Gaudi solutions are standing waves. You don't have a boundary like in this thing, okay, because we cannot make the boundary like that, but you have a topology, and this serves as a boundary. So we know that we have in general relativity standing waves. But if we think about nonlinear waves, then there is a question of definition and other things. So in general relativity, so the first people to mention this standing waves, or they call it stationary waves, was Einstein and Rosen in this famous paper. This was the famous paper on gravitational waves, when they were looking if there exist not only linear waves, but the full waves, full solutions to Einstein equations. And they found example. At the beginning, they didn't believe. They were thinking that this is counterexample, but then there were convinced that this is a really gravitational wave. They only mentioned that in this class of Einstein-Rosen solution, there is a stationary wave, but they do not study this thing. Another person who was interested in this topic is a paper by those solutions are cylindrically symmetric, and solutions that have been found by Chandrasekhar are cylindrically symmetric. But now Chandrasekhar, he was looking for standing waves. So he was looking for the whole class of solutions, and he put the assumption that he needs standing waves. There's a question how to do that, and I will explain that later. And there were other people. Stephani in 2003, Bondi 2004. So I became interested in this topic because of the Stephani paper, because it's called On Standing Gravitational Waves, and he put the question there explicitly: what is the definition of standing waves in general relativity? For Chandrasekhar, for Einstein-Rosen, it was somehow obvious what is the definition, but Stephani points out that this is not clear. Okay, so you have to specify that. And today I will analyze this Chandrasekhar solution and something that is a generalization of the Einstein-Rosen solutions of the particular member of this Einstein-Rosen class. And this particular member of Einstein-Rosen class is so-called Halilsoy solution. Now, Halilsoy was aware of this Chandrasekhar paper, so he takes a little bit from this paper, but found different type of solution. But Stephani seems to be unaware of this Chandrasekhar paper because he is using different definition of standing waves. So today I will analyze the solution by Halilsoy and the solution by Chandrasekhar. To find out what is the difference between exact solutions presented by Chandrasekhar and by Halilsoy. There are standing waves, but in according to different definitions. So, because I was interested in standing waves, the question is, what is the difference? And if you look at the full solutions, then it's hard to say. I will show you the full solutions. So what we did with Cornelia, we just linearized those solutions to look at the linearization and compare them. And this is the topic of my talk today. Okay, and now I will work in cylindrical symmetry. As I told you, in cosmology, when you have cylindrically symmetric solutions to Einstein equations, there are, in some sense, equivalent, or you can generate from them by the transformation G2 cosmological solutions because of the two killing fields, or you can go to stationary solutions and axial symmetry, but we will be not interested in that. When you go from cylindrical symmetry to cosmology or in other directions, then you have, when you find the cylindrically symmetric solutions, then you have the cosmological one, but they could have different properties. Some of them could be regular, other could be not well behaved, and so on. So there is like a dictionary between those situations, but it doesn't work 100% time. And before I studied this, I was studying the cosmological versions of these Halilsoy solutions and other things like Einstein-Rosen standing waves and the chaos in that, but this is different. Those are different topics, so I will not mention them here. And okay, so to make things clear, I don't have direct astrophysical interest in this standing wave solutions because I don't know the system that could be similar to that. The standing waves that I will study here are very simple, so there are like toy models for this phenomena. But this kind of toy models, in my opinion, could be useful because if you look at the cylindrically symmetric solutions, so there was the paper, the famous paper by Einstein-Rosen that was very influential, I would say. There was a paper by Pig and Safir, for example, where they discovered the analog of the Faraday rotation for gravitational waves. And as far as I know, I think the Riesz-Shama effect was discovered or studied at least in the cylindrical symmetry. So they are not directly physical, but they could be good toy models for something that is relevant for astrophysics, cosmology and astrophysics. Okay, so maybe I will use another blackboard here. Because I will write down those solutions, and it would be, okay, so I have to go to the top. Okay. Okay, so let's start with the Halilsoy solution. And it has the common form, you recognize it. So you have some metric functions, and dt squares, this is cylindrical symmetry. Pi squared plus I d z plus omega squared. And now this is an exact solution. So I could write down the complete solution for you, this Halilsoy solution, and it looks like this. This is given by some kind. A is the amplitude, Jo is a Bessel function of the first kind. I will use this notation to make it shorter, that all these functions have this kind of arguments. Okay, but I will not write them explicitly to make the formulas shorter. Alpha is a parameter that will be related to the polarization of the waves. Okay, and we have we need gamma function. Gamma function looks like this. Lambda is a constant. It will be the wavelength of waves. Jo J1 squared. J1 cosine squared lambda. And you still need omega function. And those solutions are not asymptotically flat. Alpha and J1 sinus. This is a Bessel function again of this with the same argument rho over lambda. And you have T over lambda here. Okay, so this is the full definition of those solutions. Now we have Chandrasekhar solution. They were given in 1986. And they look like this. Squared. So that they are similar, but you will see that they are a little bit different. This is psi with sine squared. And in this case, we don't have full exact solution. To find a solution to this system, you need to do the following thing. You have to solve equation for f. This is unknown yet function. This is a function only of function of rho. And once you find a solution to this equation, I was not able to find the exact solution to this, but you can solve this numerically. Then you find remaining functions. I will not give you formulas because they are long. You find them by quadratures. Okay. And we will be interested in linearized version of the system. So when you linearize this equation, you get the just Bessel equation. And this is Bessel equation, so it has a solution with Bessel given by Bessel functions. I will call them. So this is linearized. Okay, so you cannot see this from those equations because you don't see those equations because they are long. But if f is equal to 0, it solves this system, and this is Minkowski. Okay. So I assume the f is small, I have the Bessel equation, and I find a solution in this form. Jo, this is rho over lambda plus C2 YO rho over lambda. But now if you look at this solution and this solution, if you want to have solutions which are regular at the center, then you have to assume that at 0, this is equal 0. So, and this tells you that because of the behavior of the Bessel function of the second kind, this tells you that C2 is equal to 0. So in fact, you stay with this, where I assume that C1 is some small parameter, epsilon divided by 2. Okay, so we have both solutions. There is one more important thing about them. There is the concept of C energy. So, I mean, when you think about definition of standing gravitational wave, so it's some kind of a way where the energy is not transported in space. So this is natural definition. The whole problem is that you cannot localize energy in general relativity, and this is the whole problem with this thing, okay? But in cylindrical symmetry, in 1965, Kip Thorne suggested something that the measure of energy that it's called C energy. Now, one of the motivations of this Chandrasekhar paper was to clarify this definition, because he said that this is some kind of hand waving and this is not precise. And Chandrasekhar, he gives another justification for this C energy. I will call it EC. And in case of Halilsoy, it's just equal to gamma. And in case of, you can find this easily, this is E plus logarithm of square of phi. And now Chandrasekhar, when he was looking for the condition for the standing gravitational waves, for stationary waves, he just said that this C energy, I mean, how to justify it. So Thorne just write down Einstein equations, and using some heuristic arguments, he showed that the C energy should be equivalent of energy in cylindrical symmetry should be defined in some way. What Chandrasekhar did, when you have two killing things, then you can reduce commuting killing fields. You can reduce Einstein equations to the Ernst equation, and he found then you can derive Earn's equation from Lagrangian, so you can find Hamiltonian and relate energy to this Hamiltonian. So this was Chandrasekhar justification of this Thorne construction. And now what Chandrasekhar does in his paper, he just says that this C energy in his system shouldn't change at all. So when you take derivative in time of this quantity, it should be 0. And somehow this condition at first sight looked like too strict, yes, because you think if the C energy won't change at all, then maybe this will be some kind of a stationary solution or whatever. So when Stephani was thinking, this is Chandrasekhar. When Stephani was thinking about his condition, so he used less strict condition. He assumed that this should be equal to 0 only in the average sense. So when you look now, this is gamma is C energy, as you may see here. Gamma is here. Then you look at zeros of Bessel functions, J0 or J1. And at zeros, this dependence on cosine cancel. So you have something that is not changing in time. And if you are somewhere in between, then if you average, then you will have 0, but only on the average. Okay? So this is the difference between definition of standing waves according to Stephani and according to Chandrasekhar. Now, Chandrasekhar, Halilsoy, when he derived his solution, so he is aware of this Chandrasekhar paper. So he do not claim that those are stationary waves in the sense of Chandrasekhar, but Stephani, he is unaware of this earlier work, I think, and he is looking for example of the exact solution. So I think that what he did, it was some kind of a backward engineering. So he knew Einstein-Rosen standing wave, so special member of the Einstein-Rosen class, and then he constructed the definition such that those solutions satisfy it. Okay, so I think this is what happened, because he provides as an example of standing waves, he provides this Einstein-Rosen special member of this class. Okay. I still have 20 minutes, okay? Now I will change blackboard. No. No. This is black. Okay. So now I will linearize those solutions, but I won't show you all the details because it's a longer calculation. I need some place. So how we did the calculation. So the first thing was to identify Minkowski. And in the case of Chandrasekhar, this was easy because F goes to 0. Here, A, this amplitude goes to 0 as well, but then you won't have Minkowski in Cartesian coordinates because if you see at this E to this second line, I would say, then if you go with A to 0, then you don't get 1, but something that depends on alpha. So you have to introduce like sigma equals square root of cosine, hyperbolic cosine alpha. And then you have to change coordinates using this kind of a substitution. Sigma rho goes rho over sigma. Z goes the opposite way. And you have to change lambda. It's better to change lambda again in this way. And moreover, you have to change, when you define, you substitute for A just epsilon sigma squared, if I remember well. Then the line element changed the form a little bit, but it doesn't matter. So what you do next, you go to the Cartesian coordinates. Maybe I will not write it down. But you go to the Cartesian coordinates, then you get linearized solutions. So you get H alpha beta. When you get H alpha beta, then the whole trick is that you need to use the same gauge to compare both solutions. So we decided to use H alpha beta TT, transverse traceless gauge. This is the most common thing, but not all solutions could be put to this gauge. They have to satisfy the condition like that, beta equal to 0. And we verified that this is satisfied for both of them. And then there's a nice trick how to go to this gauge. It's in Misner-Wheeler-Thorne. You simply calculate Riemann tensor. Riemann tensor should be equal to this thing, but it's a gauge invariant. So it's, you take this, calculate this, and then, sorry, I forget about derivatives. And then you integrate this twice to get HTT AK. Okay, so now I will skip all these steps. I will just give you solutions. So let's say that this will be for Halilsoy. And here we will have the same thing for Chandrasekhar. So this is transverse, then you have 0, 0, 0, 0, 0, 0, 0. And here I will introduce auxiliary functions. Here you have like minus E lambda over X Q1. Here you have 0, 0. Here you have epsilon Q0 with minus plus epsilon lambda over X, Y. Okay, one more thing. The full formulas are complicated. So what I'm doing here. Here you have coordinate system. It's cylindrically symmetric. Okay, so I'll calculate those things for z equal to 0 and to y equal to 0. So I'm just looking at the effect of the waves along the x-axis. Then the formulas become simpler. Otherwise, they would be complicated and too long, unnecessarily too long here. I will need more space here. Okay, so this is 0. This is epsilon Q0. And this is W sine hyperbolic alpha minus W sine hyperbolic alpha. Okay, and I have to explain what are those functions. There are auxiliary functions. They are just Bessel functions with appropriate index times cosine per over lambda. And W, capital W, is a little bit different function, but very similar. So they look like this. x is just x coordinate, and Chandrasekhar h alpha beta t, z equal to 0, y equal to 0. And in fact, they have very similar structure. 1, 2, 3, 4, 1, 2, 3, 4. And this is exactly the same. Q1, this is 0, 0, 0 minus epsilon Q0 plus epsilon lambda over x Q1. And here you have minus Q1, minus Q1, and here you have epsilon Q0. Something like that, and those Q's are defined here. Okay, so as you may see, we may observe two things. One thing is that those solutions differ only. First of all, we may check if they satisfy the gauge. So this is transverse and traceless. You may see if you add this cancel with that, and this cancel, this is 0. This cancel with that. Another observation is if you go to the large x, then those terms vanish and you have just plane waves as expected in cylindrical symmetry if you go far away. And similarly for the other solution. And the difference between them is in this polarization terms. This one, and the main difference is here you have additional parameter, and then you don't have cosine as Q0 and Q1, but sine, something that is shifted in phase. Okay, but now we want to understand what does it mean. 10 minutes. Maybe I will use this part of Blackboard. So we did the following thing. We put the test sphere of the sphere of test particle. Usually you put a ring or something like that. We put the sphere. So imagine that we have a system that x, y, we are moving along the x, and here you make a sphere test particles, and you study what happened to these particles if the waves are there. So to study that, you define a point with coordinate x0, you define a curve. I mean, it has a standard. I just introduce like spherical coordinates here, and I define this curve. Then I take derivative of this tangent vector to this curve, and then I calculate the distance in this way that this is integral over 0, metric. And I, and this is the tangent vector, and this is a parameter along the curve. In this way, I mean, this is something like a local analysis. This is a standard thing that people do when they want to understand how gravitational waves work. So you take t equal to constant, and you calculate this quantity along this t equal to constant. We don't know if they are geodesic, but this is not necessary to know. They are just close points, so you assume the light goes on. So the distance, you calculate just distance along the t equal a constant hypersurface. And what you get here, it looks like this Q0, and I think I will look in papers. Okay. Cosine squared theta minus sine squared theta sine squared phi minus k. This is formula that will work for Halilsoy and for Chandrasekhar. Here you have sine 2 theta sine phi minus q lambda over x q1 sine square theta sine square phi. This is like this. No. Okay, and now this k is a new function, and it's equal to q1 for Chandrasekhar, and it's equal to w sinus hyperbolic sinus alpha for Halilsoy. And I will need blackboard. Okay, so maybe I will use another one. Oh. Okay, but we need this. We won't need this anymore, so I will clean this part of the blackboard. It will be faster. Sorry. Okay, so now you have this formula. This formula gives you the deformation of the sphere when the waves are there. But we have to somehow understand it. So one thing that you can test, you can use this formula for, here you have x, and this q depends on x, q1 and k, and other things depends on x. So you can calculate this in this limit, and you get something like that. R is the radius of, it's some kind of a small number. It could be anything. And this is 1 plus epsilon 8, 1 plus 2 cosine theta. And this is, no, sorry. No, okay, it was fine. Cosine theta, cosine over lambda. And if you will look at this formula, so imagine that you have a ball at the center and the waves, whatever, this formula is the same for Halilsoy and Chandrasekhar. The ball is just squashed like that. So this is like a standard thing. So if you cut this ball with, let's say, phi equal to pi half, then you will have a ring. And if the wave is there, so it goes like that, and then it goes like that. I mean, this should be a standard thing with a standard polarization. This is at the center. Now, the interesting thing is, I'm almost done. When you look far away, somewhere here, then what you will get from this formula, let's start with Chandrasekhar. For this formula, you will get something like that. 1 plus u theta phi x cosine p over lambda. This is, so this time-dependent factor, it factorized. And this is important because now if you look at the waves, you can see what happened. X, Z, Y, we are moving along the X. So I have some kind of a screens here. Let's say that we take this pi equal to pi 2. Then you have a linear polarization, but the angle depends on your position in space. So for example, if I will draw it here, then you have something like that. But if you will move here, then it could be shifted like that, okay? And this, I have not seen something like that for the gravitational waves before, but this is known in electrodynamics. What they call it, I have found one paper about that, they call it polarization waves. Because when you move here along the x, the polarization oscillates, okay? And this, in electrodynamics, you get this kind of solutions when you add two circular polarized waves going in opposite directions with the same amplitude and with the opposite handedness. Okay, so there are like circling in this way, and in total they make something that looks like this. And now, and of course, you still have this factor with cosine t over lambda, but it's like a position independent. So all these test particles move in the same wave along the x-axis. Now, if you do the same for Halilsoy, then you will not get this factorization. This means that when you calculate, because in order to calculate this direction, what I do, I just calculate phi equal phi half, let's say. I'm looking for extrema of that. And this solution in the case of Chandrasekhar is time independent. In the case of Halilsoy, it depends. This is Halilsoy. It depends on time. So this means that if you have this kind of a screen, maybe I will draw it in this way. Then you have like at different times, this angle changes. Okay, so maybe it's like, in fact, what this is doing, it's oscillating this way. This is the standard circular polarized wave. But because this is a stationary wave, standing waves, this angle of polarization just go in one direction and the maximum angle depends on this alpha parameter. So I think I'm done. So what is the outcome? So we had solutions to Einstein equations that were hard to analyze at the nonlinear level when you had the full solutions. What we tried to do with this cosmological counterpart of Einstein-Rosen waves, we tried to analyze geodesic deviation equation for stationary observers, but those kind of observers exist only in the cosmological solutions. In cylindrical symmetry, the central part of the wave dominates gravitational attraction, so it looks like a let's say massive strat in the center. So when you put particle, it's moving around, but because there are more waves, then it's moving like a little bit like that. So you cannot study this. But using this linear approximation, we have direct interpretation of the alpha parameter, and we can see what is the difference between Chandrasekhar solution and what is the difference between Chandrasekhar solution and Halilsoy solution. So it's some kind of a clarification. So thank you for your attention.
Now we have some time for questions.
So if you have a using two black holes and you have a final black hole that is basically excited and its excitation dies down, the interpretation for emission of gravitational waves is that we have a static wave on on the horizon of the black hole. Is it something that is possible to generalize from here to real case of a black hole?
This is cylindrical symmetry. So, I mean, so here we can see that there are these different types of standing waves. So in this sense, yes, but this is just a toy model. So I don't know how exactly to go from cylindrical symmetry to something realistic, as you said, in the case of the collision of black holes.
More questions?
I have a question related to sea energy.
Oh,
There is a question from the computer,
okay.
from
Yeah,
Professor Jagiellonian.
so I would like to understand this sea energy is a local object, a function, or something global?
It's just a local function. It's given, so you can see directly for Halilsoy solution. This is the gamma function.
So it means that you have some counterpart of density of the energy?
In some sense, yes. I don't know if it's directly equivalent to such thing, but I mean, this is sea energy, and if you ask how is it related to the true energy, then I don't know the answer, and nobody knows, I think.
Okay.
But it's useful in this way that if you see, I mean, we have linearized solution, and they are standing waves. So somehow this definition of Chandrasekhar, it worked, yes?
Okay,
But
I have another remark related to...
What is the relation between sea energy and the true energy, if this true energy could be defined in this local way? Probably not.
Okay, I have another remark related to the description of linearized gravity. If you work on a Minkowski background, perhaps it is your case, yes, that you work on Minkowski background.
Yes.
Then you have some symmetries on Minkowski background, and then you can build some objects. In case of cylindrical symmetry is possible also, which are local and describe the whole information about linearized gravity in a gauge invariant way. So you don't need transversal gauge. You
Okay,
take this
so-
metric h mu nu and you pass to the linearized Weil tensor or Riemann tensor, because this is vacuum. So try to take linearized Riemann, second derivatives of h mu nu, and then some particular components of this Riemann correspond to those true degrees of freedom of linearized gravity. So I can explain you privately how to do this.
Okay, so I will be interested.
And the geometrical object which is behind this construction is so-called conformal Yano-Killing tensor.
Okay. Thank you for comment.